Hi, and welcome to this session. Our purpose here will be to cover the snow load module within Structural Engineering Library. The format of the video will be to break things down into about four major categories. First, we'll show you how to find the snow load module and start a calculation using the module. Then we'll focus specifically on how to use the module to calculate flat roof snow loads. Then we'll have a section that dedicates itself to the use of the module for sloped roof snow loads. And then finally, we'll use the module to calculate drifts both on lower roofs and at obstructions in roofs. So with that basic intro, let's go ahead now and using this project file that I currently have open, I'm going to come up to the Loads and Forces division in the Project Manager. And then I'm going to come down to the item called Snow Loads. And if I double click that, I'll open into the ASCE 7 Snow Loads module. Now at a basic level, I just want to cover the layout of the screen here to show that there are tabs across the horizontal row where we can enter some general project information like new high school. That would be on a project level. And then notice that the other tabs are used to cover the other topics that I mentioned. So flat roof snow loads, sloped roof snow loads, drifts on lower roofs, and drifts at roof projections. And then for reference, I'd point out that we also have a drift reference diagrams tab that explains the terminology used in ASCE 7, referring to windward steps and windward drifts, leeward steps and leeward drifts, and then some of the nomenclature for the variables that are used to define drifts on roofs. So back to the General tab. The last item here on the General tab is to select which ASCE 7 version you want to use. For the purposes of our video, we'll stay with the newer ASCE 7 standard, but the differences are really very minor between ASCE 710 and ASCE 705. They primarily relate to some of the limits that are used in the formula to calculate the drifts, but the usage of the module will be fair to look at either of those standards, and you'll get the sense for how you enter data into the module. So let's consider that our basic introduction to this module. And the next thing that we'll do is move on specifically to talk about how we can use the Flat Roof Snow Loads tab. What we'll do in this section of the video is we'll demonstrate how we would use the module to calculate flat roof snow loads, assuming that we had a portion of our building that was higher than all the others, not subject to drifting for any reason, and was a flat roof condition. So this flat roof snow loads is actually the only tab that we'll need to get our answer for this kind of a snow load calculation. I would just point out that we have the option while we're on the flat roof snow load tab of defining up to 10 different conditions, and we'll see how those can come in handy as we move on to the other stages of the video where we look at calculating sloped roof snow loads and drifts at lower roofs and projections and so on. But for now, to continue with our flat roof snow load example, let's just assume that we're looking now at the snow load that's on top of a flat roof gymnasium. So we'll put in a description of gym so that this is meaningful to us down the road. Let's say that the ground snow load for our area is 30 psf according to the referenced figure from ASCE 7, and that based on a review of the terrain category for the different quadrants, we'd say that this categorizes as a C according to the reference section of ASCE 7. Again, remember this is ASCE 710 now that we're basing this on. Let's say that because of the conditions around this particular roof, we would categorize it as being partially exposed. That information leads us to an exposure factor coming from table 7.2 with a value of 1.0. Now this is another item that was changed in ASCE 710. They introduced a new item in this list for the thermal factor, so be aware of that if you're trying to acclimate yourself to ASCE 710. But let's just assume for our purposes in this calculation that The one that applies to us here is the one with a factor of 1.0, all structures that are not otherwise defined according to table 7.3. Let's just raise the risk category here to a category 3 so that we can get some interesting importance factors here. Perhaps it's scheduled to be used as some sort of an emergency shelter, or for some reason our risk category is relatively high for this gym. This section from here down performs a check for the minimum values for low slope roofs in accordance with the referenced section. So what we need to do in order to bring about this calculation is we need to provide the roof slope. Let's say that this is pitched minimally, so maybe it's only got about a 2-degree pitch to it. And then we need to provide it with the dimension that they reference as W, which is the horizontal distance from the eave all the way to the ridge. So let's say that that happens to have a value of 50 feet. And then we use the roof configuration drop-down list box to indicate whether this is a monoslope roof, or in our case what I've envisioned is that this is a gable roof. So I'll choose the hip and gable option. Now we can just drop down to the results box, and what we can see here is that the minimum required snow load based on the parameters that we've entered would be 22 pounds per square foot, but that the calculated flat roof snow load based on equation 7.1 actually turns out to be 23.1 pounds per square foot. So the design snow load for our gym roof would be either the minimum required snow load or the calculated value of the snow load, whichever is greater. So in this case, that's what we're seeing is the greater value of about 23 or 23.1 pounds per square foot design snow load on that flat roof. So that's a thorough look at how you can use the module for the very basic condition of a flat roof snow load. The next thing that we'll do is we'll take a look at how to use the snow loads module to define a sloped roof snow load. Now when we work with sloped roof snow loads, they depend on a flat roof snow load for part of their input. So let's assume that on this project that we have an entryway that happens to have a gable roof over it. So what we're going to do is on the flat roof snow loads tab to start with, we're going to select load number 2. We'll enable printing for this option or for this load. And what we're going to do in the description is just say that this is for gable entry. And then we're going to come in and set up this calculation just like we did the previous calc for flat roof snow load, except that because this is a different part of the building, we might have some slightly different parameters here. For instance, I'm going to say that the thermal factor is still 1.0, but perhaps the risk category is not category 3 like we used before, but maybe it's a category 1. It really doesn't matter all that much. But whatever we do here, we need to make sure that we define the geometry correctly. And let's just say that this is a high-pitched roof, so we'll give it a 45-degree slope, 12 on 12 pitch. And let's use a width from the eave to the ridge of 15 feet, and we'll say that this is a gable roof. Okay, so now in this box what we see is that the input that we've provided is such that it doesn't have a minimum required snow load because the pitch is so significant that the minimum does not apply. And so all we need to be concerned about is that there is a calculated value of snow load PF, which would be the flat roof snow load of 16.8 PSF. That's the first stage in using this module to calculate a sloped roof snow load. Now what we're going to do is move to the sloped roof snow loads tab, and here we'll make sure that we have a line enabled to enter our data. We will call this gable entry, and then we come to this category here that references the flat roof snow load that will be used as the basis for the named sloped roof snow load. Now we have a couple different options. One is we can check this box right here and then just explicitly specify a flat roof snow load that we want to use for the value of PF in the sloped roof snow load calculation. Alternatively, we can leave this checkbox deselected, and instead of specifying a value for the flat roof snow load, what we can do is click this button and we get a little pop-up table here of the other flat roof snow load calculations that have been defined in this project file. So what we would naturally want to do is refer to the one that was set up for the purpose of calculating the sloped roof snow load at the gable entry, which we named for gable entry. So I'll just click on that item, it populates that name, and notice that it brings over the flat roof snow load value that we saw on the other tab, which was 16.8 PSF. We've already provided it with the information it needs to select the proper thermal factor. We've given it the slope of 45 degrees. The only thing that's left for us to do for the sloped roof snow load calculation is to indicate whether it is an unobstructed and slippery condition, in which case we see a change in the value of CS, or if those are not true. So we'll just assume that that's not true for our purposes. And then finally, over here on the right, we can see the calculated value of the sloped roof snow load reported for us, and it turns out in this case to be 10.5 PSF. So if we had multiple sloped roof snow load conditions for the project, we could simply come over here and enable more lines, provide the descriptions, use either method to specify the associated flat roof snow load, make the decision about whether it's unobstructed and slippery or not, and we would have a table that would list all of the sloped roof snow load values to use for design for the various conditions. So that is the process of using the snow load module in Structural Engineering Library in a two-step process, starting with the flat roof snow load and referencing that value over here in the sloped roof snow loads to determine a design value for sloped roof snow load. Now the next step that we'll do is we'll take a look at how we can use the calculations that are provided for snowdrifts on lower roofs and snowdrifts at roof projections. In this final section of the video, we'll work with the snowdrifts on lower roofs tab, and we'll take a look at the snowdrifts at roof projections tabs. Starting with snowdrifts on lower roofs, what we can do here is use the checkboxes to enable as many calculations as we require. And then working with this first item, what we might do is put in a description like step at cafeteria roof. Then we need to provide the balanced snow load. So let's just say that that's 17 pounds per square foot. And the ground snow load, we'll use 30 PSF as a good estimate for that. We have to enter the length of the upper roof. So let's just say that that one is 100 feet long. And the length of the lower roof. Let's say that the lower roof length is 75 feet long. The last piece of information that we have to provide is what is the height of the roof step itself. So let's just assume that 6 feet is appropriate. So from here across, what we're seeing is calculated values based on the selected ASCE 7 method. So the snow density is automatically calculated for us in units of pounds per cubic foot. The program is reporting HB, which is the depth of the balanced snow load. So at the calculated density, our balanced snow load of 17 PSF turns out to be almost 1 foot deep. The value of HC is calculated and reported for us. That's the step height minus the depth of the balanced snow load. And then as part of the calculation, we need the ratio of HC over HB. So that's calculated and reported for us. Then the program takes a look at two different potential types of drift. It calculates a depth of drift for what it refers to as a leeward drift, which means wind blowing along the top of the high roof and depositing snow on the lower roof. And then it calculates the depth of what it refers to as a windward drift, which would be wind blowing along the lower roof and stalling at the step and depositing that snow on the lower roof as a result of that windward direction load. These are explained probably better in pictures than in words. So we can come to this drift reference diagrams to see that if we need to. And the key here is to just get your sense of orientation by always finding the direction of the wind. And then you'll understand the meaning of a windward step and a windward drift, and a leeward step and a leeward drift. So back to the snowdrifts on lower roofs, that got us all the way up to the value of HD leeward and HD windward. Now in a real design situation, we acknowledge that the wind can come in either direction, so either one of those drifts is potential to occur. So we have to take the maximum of those two values, which in this case is about 3.5 feet deep, and that becomes our design snow depth or depth of drift in this case. Then what we do is we move over and we look at the maximum drift intensity. This is the value called PD, and the note reminds us that this is due to the drift only. We still have to concern ourselves with the weight of the balanced snow load, so the next column gives us the maximum intensity that provides the more usable value of the drift added to the weight of the balanced snow load. So in this case we can see that we would have a total intensity right at the maximum depth of drift of 80 pounds per square foot. The ASCE 7 method also gives us a formula to determine the width of that drift, which tapers out in a triangular shape, so it would be about 14 feet, 14 foot 1. And then for convenience, we also calculate the snow intensity at the end of that drift. Now what we'll find here is that if the length of the lower roof is long enough to accommodate the entire width of drift, as is the case here where we had a lower roof that was 75 feet and a width of drift of only about 14 feet, then the total snow load at the end of the drift should be the balanced snow load. 17 psf is exactly what we provided for the balanced snow load. On the other hand, if we happen to have a long drift and a short lower roof, we might find that that drift actually ends up being truncated. And the code tells us that we need to consider it to be truncated in that situation, so it becomes a trapezoidal load. And in that situation, we'd be able to pick that up by seeing a value here that was somewhat greater than the specified balanced snow load. And that would be the design drift at the low end of, or I should say the design snow intensity at the low end of the drift where it was truncated because it wanted to extend farther than it had low roof to extend on. So that's a look at the snow drifts on lower roofs tab. I'll just jump over to the snow drifts at roof projections tab to point out that now that we've covered the snow drifts on lower roofs, this tab that covers drifts at roof projections is really extremely similar, except that you'll notice that the columns are spread out just a little bit in here because there is no need to consider both a windward and a leeward condition at a roof projection, according to ASCE 7. So we collect the same information by way of a description, balanced snow load, ground snow load. We only collect the upwind length, so LU, and the height of the roof projection itself, but notice that we don't collect a downwind or lower roof length. No need for that in this calculation, and there's some of the other intermediate calculations that drop out as well. So we end up with our HD only on the windward side of the projection, which by default becomes our design depth of drift. Then we have the maximum drift intensity, and that is due only to the drift itself, similar to what we saw on the snow drifts on lower roofs tab. We then add that to the balanced snow load so you can get a total. and we provide the width of the drift as calculated by the ASCE 7 formulas. So that is a thorough look at the third function of the snow loads module, which is to calculate snowdrifts on lower roofs and or snowdrifts at roof projections. Hope that it's been helpful. Thanks very much for your time. Take care and have a great day.